So now let's move on to some examples. Okay, so the first example is the problem that we've already looked at so far. According to early polls, candidate A was supposed to win 63% of the votes, and B was supposed to win 37%. When the votes were counted, A won 340 votes, while B won 166 votes. One of the things that I like to do just to help myself is when I think of the null hypothesis, right? When I think of the null hypothesis, I sort of write it in a sentence that the proportions of votes, right, that's my population, should be like predicted proportions. Proportions. Okay. And the alternative is that at least one of the proportions of votes will not be like predicted population. What I also like to do is I like to sort of draw this out for myself. I like to draw out the predicted population. So I'll color candidate A in blue, and so that will be about 63%. And candidate B will be in red, and that'll be 37%. And so eventually I want to know whether this is reflected in my actual votes. The significance level, we could set it at 0.05 just out of convention, and we know that it has to be one-tailed because this is definitely going to be a chi-square. And we know it's a chi-square because it's about expected proportions, right? So now let's set our decision stage. Now our decision stage, it's helpful to draw that chi-square distribution and to sort of label it and put our alpha here. And this is our rejection region, 0.05. Now it would be nice to know what our critical chi-square is. And in order to find that, we need degrees of freedom. And degrees of freedom is the number of categories. So in this case, 2 minus 1. And that's 1 degree of freedom. And it's because if you know, let's say, that candidate B is supposed to win 37% of the votes, you could actually figure out candidate A, right? Like you don't need me to tell you what that is. You could figure it out. And candidate A cannot vary, the proportion cannot vary freely once you know this one. And that's why it's number of categories minus 1. All right, so now that we have that, it might be useful to look at either in the back of your book or use an Excel spreadsheet, Excel function, in order to find our critical chi-square. So in order to find chi-square, there are two functions that you need to know, just like t-dist and t-inv, f-dist and f-inv. Now there's chi-dist, right? Actually, we need to use chi-inv right now, because here we have the probability, 0.05, and the degrees of freedom, 1. And that will give us our critical chi-square, and that's 3.84. So critical, and so this is the boundary we're looking for, 3.84. So anything more extreme, more positive than 3.84, and we're going to reject our null hypothesis. All right, so now that our decision stage is set, now it's helpful to actually work with our population. And remember, when we talk about our population, I should have left myself some room. When we talk about our actual sample, here's what we end up having. We have our observed frequencies already. So for candidate A, I'm going to write a column for observed. and candidate B. So candidate A, we observed 340 votes. So that is our observed frequency. For candidate B, we see 166 votes. Now, one thing that helps is if we know what the total number of votes was. So the total number of votes is going to be 340 plus 166, and that's 506. So 506 people actually voted in this thing. So down here, I'm going to write total, 506. Now the question is, what should our expected frequencies have been? So here I'm going to write expected. And I know that my proportion of expected should be 63%. That means if this is the total number of people who voted, so here's our little sample of 506 people, right? This is our 100%. But here we have 506 people in our sample. We should expect 63% of 506 to have voted for A, right? And so how do we find that? Well, we're going to multiply 63% to 506 to find out how many votes that little blue bit is, right? And so that's going to be 0.63 times 506, that total amount. See, if we multiply 506 by 1, we would get 506, right? So if we multiply it by a little bit of a smaller proportion, then we get just that chunk. 318.78. Actually, I am going to put this here. Let me actually draw this little table right in here, because that's going to help us do our find our chi-square much more quickly. And so observed, expected frequency, observed frequency is 340 and 166. Okay, so what is our other expected frequency for B? So in order to find this little bit, we're going to multiply 0.37 times 506. So 0.37 times 506. And that's 187.22. And usually, if you add this entire column up, you should get roughly a similar total. When you do it, when you do these by hand, sometimes you may not get exactly the same number. It might be off by just a little bit because of a rounding error, right? Because if you round to the nearest tenth or you round to the nearest integer, you might get a little bit of a rounding error, but you shouldn't be off by much. So that's one way you could check to see what you did was right. And so once we have this, so let me just copy these down right here. So 318.78 and 187.22, right? And for each of these, the total is 506. So here, one of the things we see is that the expected values for A are a little bit lower, and the expected values for B are a little bit higher, right? But is this difference in proportions, is that significant? Is that standing out enough, right? And in order to find that, we need to find the chi-square, the sample's chi-square. Now, I've completely run out of room here, but I'll just write the chi-square formula up here. So the chi-square is going to be the sum over all the categories of the observed frequency minus the expected squared as a proportion of the expected frequencies, right? And so what I'm going to do is calculate this for each category, A and B, and then add them up. So right here, I'm going to call this a column O minus E squared all over E. So I'm going to do that for A and B, and then sum them up. So my observed minus expected squared, all divided by expected. And so here I get this proportion, and I'm just going to copy and paste that down here. And then here I'm just going to sum them up. And I get 3.817. Ooh, we're really close, but no cigar. So we're right underneath. So our sample chi-square is just a smidge smaller than our critical chi-square. So here we're not rejecting the null. We are going to fail to reject the null. So let's find the p-value. So in order to find the p-value, you could use chi-dist, or alternatively, look it up in the back of your book. Look for the chi-square distribution. It should be behind your normal, your t, your f, and then chi-square should come right behind it, right? So usually it goes in that order. Maybe it's slightly different order. And our degrees of freedom remain the same, 1. And so, our p-value is just over 0.05. It's 0.05, if we round, 0.051, right? So because of that, we are not going to reject the null. So we're going to say, hey, the proportions of votes are roughly similar to the predicted proportions. Well, they're not significantly different, at least. They're not super similar, but we can't make a decision about that. But we can say they're not that different from this. They're not extremely different, at least. Ta-da. Okay, example 2. A study asked whether college students could tell dog food apart from expensive liver pâtés, liverwurst, and Spam. God, I don't even know what liverwurst is. All were blended to the same consistency, chilled, and garnished with herbs and a lemon wedge, just to make it look pretty. Students were asked to identify which was dog food. Researchers wanted to test a probability model where the students are randomly guessing. How would they test their hypothesized model? Okay, so see the download that shows how many students picked that item to be dog food. So it seems that college students have a bunch of different choices. They have dog food, liver pâtés, liverwurst, and Spam, right? And then they need to identify which was dog food. So out of those, which of those is dog food? So sort of like a multiple choice question. So if you hit example 2 in the download that's listed below, you'll see the number of students that selected that particular item as dog food. Now, be careful, because some people right here, remember, you might get this problem on a test and you won't know that it's a chi-square problem. Sometimes people might immediately just think, I'll find the mean, right? And so they just go ahead and find the mean. But then if you do find the mean, ask yourself, what does this mean, right? What is the idea or the concept? If we average this, we would find the average number of students that selected any of these items as dog food. And that's sort of a mean that doesn't make any sense, right? And so before you go ahead and find the mean, ask yourself whether the mean is actually meaningful, right? So here, we know that it's a chi-square because the students are choosing something, and it's a categorical choice. They're not giving you an answer like 20 inches or 50 degrees or I got 10 questions correct, right? They're actually just saying that one is dog food, right? And they have 5 different choices, and they've chosen one of them as dog food. So out of 5 choices, a probability model that they're just guessing would mean that 20% of the time they should pick pâté 1 to be dog food, 20% of the time they'll pick Spam to be dog food, 20% of the time they'll pick dog food to be dog food, and so on and so forth, right? So let's draw that probability model. and by model, we often mean null hypothesis, right? Model or hypothesized population. So step 1. So the null hypothesis is the idea that they will fit into this picture. So if this is the population, right, and it's out of 100%, and they have 5 choices. Oh, my picture is just slightly uneven. It helps to really draw this as well as you can, just because then it'll help you reason too. That they'll have an equal chance of guessing either one of these. And there's 2 liver pates. That's why there's 5 choices, right? So liver pate 1, liver pate 1, I think Spam was next, and then actual dog food, just in the data set. What was I forget. Oh, pate 2, and then liverwurst. So I'll say pate 2, and then liverwurst. All right, so these are the 5 choices, and we're saying, look, the students are just guessing. They should have a 20% probability of each. Is this the right proportions for this sample? Is the sample going to sort of match this or be very different from this? The alternative is that at least one of the real proportions is different from predicted. Okay, so once we have that, we could set our alpha to be 0.05. Our decision stage, we could draw chi-square, right? And our degrees of freedom, we now have 5 categories. And so our degrees of freedom is 5 minus 1, which equals 4. And it's because once we know 4 of these, right, then we could actually figure out the proportion for the 5th one just from knowing 4 of these. So that one is no longer free to vary. It doesn't have freedom anymore. It's sort of locked in. Okay, so what is our critical chi-square? Well, if you want to pull up your Excel data. Here, I'm just going to start off with step 3. In step 3, our critical chi-square. In order to find that, we could use chi-inv, put in the probability that we're interested in, and our degrees of freedom, which is 4. And so our critical chi-square is 9.449. 9.49. Notice that as degrees of freedom goes up, right? As degrees of freedom goes up, what's happening to the critical chi, what's happening to the chi distribution is that it's getting fatter. It's getting more variable. And because of that, we need a more extreme chi-square value. So that's sort of different than like T distributions or F distributions. There, those distributions got sharper when we increased our degrees of freedom. Chi distributions work the opposite way. Those chi distributions are getting more variable as degrees of freedom goes up. Okay. So once we have this, now we could start working on our actual data, our actual sample. So step 4 is we need to find the sample's chi-square. And in order to do that, it helps to draw out that table. So the table might look something like this. I'll just copy this down here. Right? And this is the type of food. Right? So that's the category, right? And here we have our observed frequencies, the actual number of students that pick that thing to be dog food. So here we see 1 student pick pate 1 to be dog food, 15 students picked liverwurst to be the dog food. what are the expected frequencies? Well, in order to find expected frequencies, we know that the expected proportions are going to be 0.2 all the way down, right? 20%, 20%, 20%, 20%, right? And here, I'm just going to total these up. Sum, total, same thing. And I see that 34 students were asked this question. Our expected frequencies should add up to about 34. Our expected proportions add up to 1, right? And that's why we can't just directly compare these two things yet. They're not in the same sort of currency yet. You sort of have to change this currency into frequencies. So how do we do that? Well, we imagine here are all 34 students. Take 20% of them. How many students will that be? So that's 0.2 times 34. This times 34. And I'm just going to lock down that 34 because that total proportion, sum won't change. So this is what we should expect. That's if they were indeed guessing. This is the expected frequencies that we should see. And if I just move that over here, we'll see that that column also adds up to 34. Now, once we have that, we can compute our actual chi-square. Because remember, that's observed frequency minus expected squared divided by expected as a proportion of expected. So that's the observed frequency minus expected frequency squared divided by the expected frequency. And I could take that down for each row and then add those up. And here I get my chi-square statistic for my sample. And so my sample chi-square is going to be, I'm just going to put a pointer right here, is 16.29. And that's a larger, more extreme chi-square than my critical chi-square, right? And so let's also find p-value here. In order to find p-value, I could use chi dist. Here I put in my chi-square and my degrees of freedom, which is 4. And so that's 0.003, and that is certainly smaller than 0.05. And so in step 5, we reject the null. Now I just want to make a comment here. Notice that here, after we do the chi-square, although we reject the null, just like in the ANOVA, we don't actually know which of the categories is the one that's really off. When we eyeball this one here, we could sort of see this one probably seems to be the most off, but we're just eyeballing it. We're not using actual statistical principles. So once you reject the null, there's post hoc tests that you could do, but we're not going to cover those here. All right, so it seems that students are not randomly guessing. They actually have a preference for something as being dog food. My guess is liverwurst. I don't even know what that is. Okay, so example 3. Which of these statements describe properties of the chi-square goodness of fit test? Okay, so if you switch the order of categories, the value of the test statistics does not change. That's actually true. It doesn't matter whether candidate A got added before candidate B. Addition is totally order insensitive. You could add A then B or B then A. You could add pate then liverwurst then dog food, or dog food then liverwurst then pate. Sort of doesn't matter, right? So this is actually true. That's a true property. Observed frequencies are always whole numbers. That's also actually true, because when you observe the frequency, you're actually counting how many category members you have. So counting is going to be made up of whole numbers. Expected frequencies are always whole numbers. That is actually not true. Expected frequencies are predicted frequencies. It's not that at any one time you'll have 6.8 students saying that liverwurst is dog food, but it's that on average, that's what you would predict given a certain proportion, right? And so this is actually not true. Expected frequencies don't have to be whole numbers because they're theoretical. They're not actually things that we counted up in real life. A high value of I almost said x squared, of chi-squared indicates high level of agreement between observed frequencies and the expected frequencies. Actually, if you think about the chi-square statistic, this is actually the opposite of what is actually the real case. If we had a high level of agreement, this number would be very small. And because this numerator is small, the chi-square would also be small. A high value of chi-square would actually mean that this is quite large compared to this, right? And so this is actually also wrong. It's the opposite. All right, so that's it for chi-square goodness of fit test. Join us next time on educator.com for chi-square test of homogeneity.